Hi everyone, thanks Boumediene for inviting me to talk here at Cambridge. It's been about 20 years since I last came, so, so it's the first real visit to meet for me. So I'm going to be presenting this work on Gaussian processes simplify differential equations. It's actually an amalgamation of three different papers. The first one, which has this title and was submitted to Physica D, and it's currently a preprint. The second one on recruitment operators was published earlier this year, and the third one on Lyapunov functions was submitted to a conference in Iceland, which took place last week. So this is joint work with my Boumediene, of course, with my current advisor Human Awadi at CALTECH, and some other collaborators. So I'm going to first talk about the motivation for this work, which is which is basically the topic of my PhD. So this is about trying to simplify or trying to make nonlinear dynamics more interpretable in some sense. So there are some reasons why people are interested in doing this in like applied mathematics. And there are also a number of methods. So people might be interested in trying to directly map the solution of one PDE to the solution of another PDE, which may be like, for example, from a nonlinear PDE to a linear PDE, as we're going to talk about today, which is like one example. And then another part of this talk is going to be devoted about mapping this trajectory of one nonlinear ODE to the trajectory of something which is also nonlinear but has simpler behavior. So the first one, the call-off transformation, is going to be a global transformation. The second one, which is about Poincare normal forms, is going to be a local one, which is around the equilibrium of the dynamical system. I'm going to talk a bit about the method we use for this simplification. So we're going to be talking about Gaussian process regression or kernel regression. They're two sides of the same coin. And we use it for all the examples I'm going to talk about in this talk. So the reason why I've been focused on kernel methods instead of, say, neural networks is that kernel methods have this nice properties such as like nice convergence bounds and convergence theorems like error bounds. And it's also more interpretable in this sense. We're also going to talk about the difference between the classical kernel regression, which you may have encountered in like machine learning, and the generalized version I'm going to talk about today. And also we're going to talk a bit about how we're going to learn the optimal parameters for our kernel we use in one of our examples. So this is a very well-known example of a direct global transformation from a nonlinear PDE to linear PDE. This is the Burger's equation over there, which is a famous nonlinear PDE. It's known because it has shocks, and that makes it a bit nasty in some sense. The second equation is even more well-known, the heat equation. And the call-off transformation is a very rare example where you have this closed-form relationship between two famous nonlinear and linear PDEs, respectively. So there are two versions which you often encounter in the literature. So there's this version which takes the spatial derivative of the heat equation and the heat equation, the solution itself, and you get this relation to get the Burger's equation. And then there's this other form we're going to focus on today, which is which takes the antiderivative of the Burger's equation, which itself is also a solution of a nonlinear PDE, and we map it to the solution of the heat equation. So there are a number of different forms of the call-off equation. This one is the one which is most famous, but since this heat equation has this nice property, which means that if you take a linear transformation of a solution of the heat equation, then you get another solution. We're going to actually learn this one because it has this nice property such that d of 1 is equal to 0 and d of 0 is equal to 1. So just a quick introduction about the people who made this, who discovered this call-off transformation. Julian Cole was actually a student at Caltech, my university, and this was actually the subject of his PhD thesis in 1950. This is Eberhard Hopf, not to be confused with Alexander Hopf, who's the guy behind the Hopf algebras. And yeah, he also discovered this around the same time. Yeah, so how do we map or learn this Koloff transformation? Okay, so let's say you have the initial condition of the Burger's equation, and then you can just use this Euler-like scheme to to advance it forward in time by one time step. And then you do the same thing for the heat equation. And yeah, and the nice thing is, this will be clear in the diagram I show you next, in the next slide, is that you can go from W1 from V0 in two different ways. Yeah, so you can go from via this route where you first apply the Euler scheme to the Burger's equation, and then you do this integral, and then you apply this Koloff transformation, and then you get to W1. Alternatively, you can go this way where you start from V0, then you apply the integral, and then you apply the Koloff transformation, and then you advance the initial condition of the heat equation by one time step. So you can exploit this relationship and formulate the following optimization problem. So those of you who are familiar with the kernels and RKHS, or reproducing kernel Hilbert spaces, will find this somewhat familiar. Those of you who aren't, the way you can think about this is that you're trying to find a sufficiently regular function which satisfies these constraints. The first two come from the diagram in the previous slide. The second, the third, and the fourth, they're pretty much arbitrary. You can replace these numbers with any other real numbers, but you get a different version of the Koloff transformation. And we put them there because otherwise the solution of this problem is going to be 0. Now the entire, this of course depends on the kernel you use. We use the Matern 2.5 kernel since this is a more general or like smooth kernel which doesn't have many assumptions about the structure of your data. So this is pretty much the next step of what we're going to do. We combine the first two constraints from the previous slide into one. So we merge it, and then we're saying that we want this to be satisfied at each of our collocation points. We have n of them in total, and then we keep the uniqueness constraints in place. And then the next one is pretty simple in the sense that you just take the limit as the time step h goes to 0, and then you formulate a differential equation. It's a second order ODE, which is why we have those two uniqueness constraints, not one. And then here's the nice part. This is just a linear differential equation. And the really nice thing is that it has the solution we use, the kernel regression solution, it has this nice formula. So this is what we call the generalized representative theorem. Those of you who are familiar with the classical representative theorem might find this somewhat similar, but the main difference is that in the classical version, you have a number of data points, and then you observe an output at each of those data points, and then you try to find the function which best describes the relationship between the input and output. In this version, it's slightly different. It's instead of observing the values of the function directly at your collocation points, you end up observing the action of this bounded linear function, or in this case, a differential operator at this point, and you still get something similar. So this, if you're familiar with Gaussian processes on Banach spaces, you can think of this, both the classical and the generalized representative theorems, as the conditional expectation of an unknown function, which you approximate by a Gaussian process given a bunch of observation or information. So the rationale behind this formula, I'm going to go a bit more in detail. So Y comes from the constraints from the optimization problem we had on the previous slide. And then this K5 phi is a matrix whose entries are just the kernel evaluated at a bunch of, at each pair of collocation, not actually the kernel evaluated at each collocation points, but rather this linear function applied to the kernel evaluated at a bunch of collocation points. And of the antiderivative of the Burgers equation. Here we're going to keep it much more general, and we assume that we have this nonlinear PDE, which is a function of u, the solution, and a bunch of derivatives in space. And then, again, like before, we have this linear PDE, which is a function of the output of a linear differential operator on the right-hand side. And then, again, we also want to have some sort of, we also assume that there exists a map which maps the solution of the first one to the second one. This should be a V, not a U. There should be some consistency over there. And we assume that the possible inputs of this function we're looking for are the solution of the nonlinear differential equation, its derivatives in space, and potentially antiderivatives as well. So we do something similar. We're going to say that we advanced U0 by 1 time step, the same for V0. And then we're going to use this commutative property of this diagram to formulate this differential equation once again. So we end up with something like this, which is much more general than what we had for the Koloff transformation. And then we also need a uniqueness constraint at the bottom to prevent the whole thing from going to 0. So this is what we're actually trying to look into from this autumn onwards to see what happens. Can we just take a nonlinear PDE and then map it to a linear PDE in this the same fashion as we did for Koloff? And then, okay, you might ask me, okay, how do you know there actually exists a transformation? What happens if you don't even know what you're transforming to? And this is where it becomes even more general. You have to now minimize the sum of the RKHS norms of T and also the L, the linear operator. And this is the most advanced case, which we haven't looked into yet, but this is something which we're going to start exploring. So again, another question is, how do you know how many inputs you need for this thing to work, and how do you know if this transformation holds at least like locally? So we can just start with one like input, such as just the solution of the differential nonlinear PDE, and then if there's no like function which satisfies this optimization problem, then what happens is that the RKHS norm you observe is going to blow up and go to infinity as the number of collocation points increases. On the other hand, if there exists a transformation, you'll find that the RKHS norm will actually converge or flatline as the number of points goes to infinity. And this is how you might start exploring this. So I think the whole point of this Koloff exercise is that although Koloff is a very well-known example of a direct transformation between a nonlinear PDE to a linear PDE, there might be other ones out there in the universe which may not have this nice simple formula, but it could be the case that we can find a function which maps the solution of one to the solution of another. As for normal forms, this is still an active direction of research, which I'm doing with Boumediene right now. So the next steps are to also explore, as I said, the more general case where you map like families of trajectories to families of other trajectories, and also inner product normal forms where you try to, instead of doing the Poincaré approach, where you try to find an appropriate inner product in the polynomial space, which eliminates the maximum number of terms. And yeah, so there are many exciting things we can go from here, but I'm going to move on to the next section of this work, which is learning Koopman eigenfunctions and its applications to learning or constructing Lyapunov functions. So Koopman operators are another tool for analyzing nonlinear dynamical systems. It basically maps a nonlinear dynamical system to something which is linear but in infinite dimensions. So a lot of people try to approximate this infinite dimensional operator with a matrix, we try to sidestep that, and we try to instead analyze Koopman operators by learning its eigenfunctions. So again, we use kernel methods because it has this nice like error-bound property, which we're going to show one of them later in this during my slides. So some of you may be familiar with Koopman operators if you work in this field. For those of you who aren't, the Koopman operator is basically the composition of this measurement function or an observable, which is an element of a Hilbert space, and the flow map of the dynamical system. So what's so nice about the Koopman operator is that it has this nice property in which we can express this as a differential equation, and there's another thing called the infinitesimal generator of the Koopman operator, which tells you like, okay, let's advance the dynamical system by a very small amount in time. How much is like g going to change if you as t goes to 0? And then we define something called the Koopman eigenfunction, which is a linear PDE in terms of phi lambda. There are infinitely many eigenfunctions and eigenvalues. We consider a particular case of eigenfunctions called the principal eigenfunctions, since people have found that they have many useful properties in learning or in analyzing nonlinear dynamical systems, such as stable and unstable manifolds and other things like zero-level curves. So, so how do we try to learn or like recover the solution of this Koopman eigenfunctions with kernels? So we find that you can decompose the eigenfunctions into linear and nonlinear parts. The linear part is easy since W is just the left eigenvector of E, which is just the matrix encoding the linear part of the dynamical system. For the nonlinear part, we find that you can express this as a you can express the solution of the nonlinear part, and you can formulate a linear PDE in terms of H. And the nice thing is it's basically the same as what we did for call-off. We try to look for a function which is contained in the RKHS, and which satisfies the properties such that the PD is satisfied at the collocation points, and also these uniqueness constraints are also satisfied. So I'm going to go over a couple of examples. The representative formula, you've already seen this before. It's the same principle as what we did last time. So I don't think I'll dwell on it again here. But what's nice about this is that it has this nice stability bound, which if you look at this each term, you'll find that in our case, where the equilibrium point is set at 0, these and also the derivatives of the of h are also 0 at the origin. The second two terms on the right-hand side are going to be 0. And then this dh term is basically a term which kind of enforces or measures how well this PDE is satisfied at the collocation points. So this is actually a very nice property to have. There's this other property which is like a convergence or an error bound in LP space. This really depends on the fill distance and some constants over there, the dimension of the dynamical system, and also the Sobolev norm as well. And yeah, the fill distance is basically, if you're not familiar with the term, it's basically a measure of how well your collocation points explore the domain of interest. So if all of your collocation points lie in a small neighborhood of each other, and then you try to extrapolate the solution of the PDE to some region not covered, then it's not going to be very good. So we want to have these the collocation points to like well explore the domain. So we're now going to talk about a couple of examples. So there's this dynamical system here. The nice thing is that the Koopman eigenfunctions have an exact or analytical formula for each of our eigenvalues. So this is nice, which since allows us to compare the performance of a kernel solution versus the true version. So I've written a relative error to the right. I was meant to include it, but somehow it kind of got omitted. We used the Gaussian kernel, and this already performs pretty well. We didn't learn the kernel the kernel parameters this time, but again, we can use the same kernel flows approach to find the optimal parameters if we want to. So again, this one is pretty accurate. So this is for the first eigenfunction of this dynamical system. And then this is also for the second, the same example, but for the second eigenfunction. And then we also included another example in our slides. For the actual paper itself, we also included the Duffing oscillator, which is another famous 2D dynamical system and also a 3D system. But I feel like these two examples are nicer since you have an analytical formulas for the true eigenfunctions, so it's more illustrative to see the performance. So this is, again, the eigenfunctions we learn. So we learn the nonlinear part by solving the PD, and then we just add the linear part at the end. And then I'm going to talk about the final part of my talk, which is about constructing Lyapunov functions using the Koopman eigenfunctions. So people have tried, so Lyapunov functions is just a function which satisfies these properties so it's positive at everywhere other than the origin, and it's 0 at the origin, and it's v dot, which is just a gradient of vx dot f of x is going to be less than or equal to 0. So it's pretty much useful in dynamical systems theory because people use it as a tool to study the stability or instability of equilibrium points, and also to estimate the Bayesian of attraction. There's this nice theorem from a long time ago, which is basically an existence theorem saying that this Lyapunov function exists if all the real parts of the eigenfunction of the eigenvalues of the Jacobian evaluated at the origin are negative, and then there's also this what people try to do is people have done in the past is they try to construct Lyapunov functions from like RBFs, like radial basis functions. We're going to instead use the Koopman eigenfunctions we constructed from the previous section to construct Lyapunov functions, as it gives us Lyapunov functions which is more grounded in the dynamics than just using arbitrary like exponential functions. So how do we do this? We find that if we select a matrix P which satisfies this inequality here, and we construct the Lyapunov functions this way, then it's pretty simple to show that the properties over there are satisfied. And then we can do something similar for learning V dot. We take our Koopman eigenfunctions for the dynamical system, and then we use the product rule and also the Koopman eigenvalue property to get this relationship. So we included a single example for the conference paper. For the actual full journal paper, we're going to add more examples. But this is a nice example where we have true Koopman eigenfunctions, and then all the eigenvalues are real and negative. And we try to learn the eigenfunctions first using the kernel method we discussed earlier. And then we compare what happens if we do construct the Lyapunov functions using the learned eigenfunctions versus what happens if we construct them using the analytic version of the eigenfunctions. So this is really, this is for V dot as well. Somebody asked me, how do you know that this kernel regression formula will be accurate enough such that this property for the kernel, these properties of the Lyapunov function to hold? The answer is yes. If your kernel parameters are chosen badly and it's pretty inaccurate, then you can end up with cases where the V ends up going below going below 0, And similarly, you might end up with cases where v dot might end up slightly above 0. But this is why like learning or choosing suitable kernel parameters is very like important. Yes, so there's another paper on Koopman eigenfunctions, which I didn't present today, but it's learning quasi-potential functions of stochastic dynamical systems. This was also submitted to Physica D. And yeah, the nice thing about this part of my presentation is that we like bridge together kernel methods, Koopman operators, and also Lyapunov functions, which people have generally tended to consider like 3 separate fields, and we combine them together. And yeah, so thank you for attending my talk. I'm going to just, I don't know how many minutes I have, Median, but... Oof, yeah, yes, of course. So something I didn't present today, but I feel might be worth like mentioning is that I'm at the end of my 3rd year of my PhD. For the remaining 2 years, I've really been, I mean, for the past year, I've really been focused on using kernels for reduced order models for partial differential equations. So a reduced order model is basically like, you can think of it as a fast PDE solver. So when you have many points, many qualification points, and you want to solve the PDE, if you use a classical solver, it might take very long. So we're trying to use our method for solving PDEs with kernels and also combine it with method for sparse Cholesky factorization of kernel matrices to make this entire calculation like much more efficient. So that's one part of what I'm doing for my research. And then another theme is to continue exploring transformations, both between PDEs and ODEs as well. Yeah, so thank you very much. Yeah.
So you found that learning that one type of parameter in the imaginary kernel made a big difference.
Yeah.
I'm curious, would there be challenges, or what would the challenges potentially be in trying to do even more expressive kernel learning?
So we've done this in another paper on, so Boumediene also knows about this as we've collaborated. So yeah, so it's actually pretty fast learning, doing this optimization where you have multiple parameters. We've had like kernels for another paper where we have like 24 parameters, and it's pretty fast. It's all like kind of done like parallel, where we store the parameter values in a vector, and then we just calculate the derivative of this loss function with respect to each parameter.
And I guess as a follow-up question, let's just say hypothetically you had this like super flexible approach to kernel estimation that works well, like
Yeah.
any kernel function,
Yeah.
not just some few parameters of some family of kernels, but
Yeah.
really, any kernel. Reliably, would there potentially be some interpretability associated with that, like some sort of scientific insights that you might be able to derive in some of these settings about like, oh, this kernel works really well and it's telling me something about this problem I didn't already know?
Yeah, so I think generally, like, it really depends on whether you have some like a priori knowledge of what the function you're like estimating is going to look like. If it looks like a sort of like polynomial, then you might use a polynomial kernel, etc. But let's say you have no knowledge, and then you just use the kitchen sink approach of just stacking lots of kernels and adding them together. So yeah, so I think Boumediene has also done some research on this, but where we start with a very large like combination of kernels, and then you kind of eliminate the ones which don't contribute much to the loss function. Is there like a more scientific approach? I would say.
I mean, not necessarily scientific approach to learning the kernel. I'm just imagining sort of like an ideal universe where we can just learn any kernel and it's fine. You don't need to compose them together or whatever. You can just like flexibly estimate this kernel function, and it really tells you something that works well for that problem. Is there potentially sort of some set of problems where that could lead to some enhanced scientific understanding of what you're modeling? Like, just as an example of that, like
Yeah.
in your case with the imaginary kernel, if you learn the light scale and you find that, okay, performance is super sensitive to the light scale,
Yeah.
and there's some set of values that really works well,
Yeah.
then maybe that tells you something about the rate at which the function is varying, and
Yeah.
maybe there's some scientific interpretation of that. But if we were to kind of move beyond that, it's like, okay, for whatever reason, the rational quadratic or something else,
Yeah.
like just the perfect kernel for that problem. Is there sort of something that we might be able to learn from that in terms of the actual data that we're modeling?
Yeah, it's a good question. So if I think of it this way, yeah. So if you're saying that the rational quadratic kernel is like the like perfect kernel, like can we
Or
like
maybe there's some non-stationarity or something else. Like, is there something that's sort of like, it's like, okay, we've learned a non-stationary kernel, and like there's something interesting about it.
yeah, I suppose this might come up in like some like say time series analysis where you like observe a like particular trend for up to like time t equal to big T, uh, and then you want to see if it like continues, and then if you find that this like kernel like works very well for up to time t equal to big T, then you might say, okay, then it's probably best to continue using this kernel. Or do you mean something different?
Yeah, I was just thinking, like, I mean, one thing I'm very excited about is like being able to learn something about the data that we didn't already know by doing something like kernel estimation. So
Yeah.
I was just kind of generally curious, like
Mm-hmm.
in some of these applications, is there an opportunity to do that? And maybe are there some examples of where we could do that?
Okay. Yeah.
No, it actually it was saying we had some specification, right? And one time we get rid of the template.
Yeah. Yeah. Yeah.
Sometimes you just get not trigger the camera payment, but it's just happening.
Yeah. Mm.
I mean, maybe one example of where this has been done in the past, not with
Mm-hmm.
PDEs or differential equations, but in astrophysics, is like if you can learn the kernel associated with modeling light intensity from stars, you
Yeah.
can kind of reverse engineer their density profiles and
Mm-hmm.
things like this. And so this will give you some sort of scientific insight just by learning.
Yeah, it's not something I've like encountered in my current research, but like actual like industrial applications. But it's definitely something I could like look into since my professor has a lot of collaborations with people at the Jet Propulsion Laboratory, like in NASA. They actually look at doing things like learning like the shape of Jupiter's rings, and or like the sort of things like yeah yeah other like applications in astrophysics, which I can't think of off the top of my head, but yeah, it's definitely the opportunities are there. Yeah.
Question like for the first part of the talk.
Yeah.
When you map like one say nonlinear system
Yeah, of course.
to one that is a linear differential equation. So what would happen if the original system was say chaotic?
Yeah.
So where you have extreme sensitivity,
Yeah.
and then perhaps your target system is quite smooth.
Yeah.
What would the method still work, or what would you think happens when you have a problem like that?
Yes, I think the entire use is for like simplifying very like chaotic dynamical systems,
I
but,
mean, I
but
think I'm not talking about simplifying. I'm more than also wondering about accuracy,
yeah.
where I guess because the target system is somehow smooth, while the original one may not be.
Yeah.
In the sense you're then hiding away all the transformation.
Yeah, it's yes.
Iron out the kinks in a way.
Yeah.
So does that mean that learning the mapping gets more difficult if you enter into cases like that?
Yes, I would say so. It's would probably get more difficult, especially if you're trying to learn, for example, like a family of like a map, like from a like family of very chaotic stuff to something which is like very smooth. Yeah, I would say especially. I haven't tried it myself, but this is definitely something I'd be interested in doing, where you try to like map like entire families of very chaotic stuff, and then try to see if there's a family of something much nicer, and see how this affects the quality of the map.
So, is there any theory about the existence of such maps? So,
Yeah, so there have to be like some sort of topological equivalence or some like differential morphism between the systems.
okay, so what happens happens if a map doesn't exist?
So and then you if a map doesn't exist and you try to learn it using kernels, what would happen is that if you add more and more collocation points and then you try to fit a map using the kernel, using this optimization problem, the loss function is going to just blow up and go to infinity.
So essentially, then the solution becomes useless.
Exactly. Yes.
We tried to do it for the same, so not your PDE, and instead of mapping to.
Like we try to.
We tried to map it to another.
Yeah. So we. And similarly, instead of trying to map like burgers to heat, we try to map from like Kuromoto Severstinsky to heat, and then you can see a similar trend in the sense that the RKHS norm just blows up.
So I guess you may want that
Yeah.
but if it doesn't, then
Yeah.
just
Any more questions? Thank you.